Welcome to CCS5. This is Computer Architecture and Organization. For those who haven't been my students yet, my name is Ray. I'm going to be your instructor. And so this is a 3-unit course, pure lecture, so no laboratory. We have 8 hours of contact every week. So that's 4 hours Mondays, 4 hours on Thursdays. Now the prerequisite for this is CC10, Introduction to Networks. So you should have taken CC10 already. Okay, so for today we're going to have the course plan and also lectures of Unit 1 and Unit 2. Right? So for the course description, as you can see, this is an integrated approach to the concepts of hardware architecture, organization, and operating systems. Now our topics would include the fundamentals of computer design, introduction to computer OS, and an in-depth discussion of instruction set principles. These are the different outcomes. Now, there are 2 outcomes here that I marked with an asterisk, which means that I'm not going to require this from you. I usually require this from all CCS5 classes, including last year. But since we're in a pandemic and the mode of delivery is online, I decided to not go through with your course project, which is supposed to be an international or national publication. So I decided to opt that out, okay? Because I think you're going to have a hard time if I include that, especially that we have this new way of delivering the courses with the first half and second half, okay? So anyway, for the course outcomes, at the end of the trimester, you're supposed to be able to, number 1, differentiate and compare computer architecture structures, as well as OS varieties, performance, advantages, and trade-offs. Second is to adapt to the quantitative approach related to design and performance of computer systems. And third is to infer how hardware design considerations affect the development of software systems, including the operating systems used on specific hardware. Okay, so the 4th and 5th supposedly here is for you to conduct a research of how various scheduling algorithms help operating systems maximize hardware architecture. And you're supposed to present or submit these researches to a national or international conference, which is Scopus Index. But like I said, we're not going to do this anymore. But I'm sure that some of you are aware that last year I had successfully published 5 papers. 11 papers from the class were accepted to China and Japan for a conference, for 2 conferences, but only 5 groups were able to go. So it would have been good to have your batch have the same experience, but since we have an online distance learning, we really can't travel anyway. So I just opted to leave out the research part of the course. Okay, so we'll just focus on the academics of the course, right? So this is the breakdown of the units we're going to have. For the midterms, we're going to have units 1, 2, and 3. So unit 1 is just fundamentals of computer design. We have introduction to design, classes of computers, and defining computer architecture. So that's the first unit. The second unit is all about power, static power consumption, and integrated circuits. That's also going to be in the midterm. And the third is about quantitative principles of design and measurement, specifically on modules and integrated circuits, right? So we have module dependability and reliability, measuring performance in integrated circuits, and quantitative principles of design. Now those are your 3 units for midterms. For the finals, we're going to have another 3, which now switches into an overview of operating systems, the operating system kernel, what are system calls, what do they do, why are they important, and the components of operating systems. Then we go through different architectures of operating systems and how they relate with hardware. We have monolithic, layered, virtual machine, and microkernel. And then on the last part, we're going to focus on instruction set principles, where you have classifying instruction set architecture, memory addressing, and up until MIPS instruction set. Okay, so for the midterms, mostly we're going to talk about hardware, and then the closest software that works together with your computer hardware is the OS. So during the finals, we're going to talk about the OS and different types of architectures of the OS. Although you have a different subject during your third year, separate for which focuses on operating systems, we're going to tackle the overview in this course, right? So the time frame for our course is this. This is just a suggested time frame of what we're going to do. Okay, so since it's ODL, I can't really manage the time, your time, so you manage it on your own. No? So walang sisihan. Okay, I give you instructions, I give you activities and lectures, and you manage your own time to accomplish those activities. Okay, but if you want to follow this suggested lecture time frame, then it's fine. Okay, so supposedly I'm going to post a lecture recorded every every Monday, sorry, 11:30, and you're going to watch that until 1 o'clock or however long the video is. Okay, so I'm going to post that in Canvas, but it's going to be a URL uploaded to YouTube, like I posted on the Facebook group. Okay. Now, after you watch the lecture, I encourage you to do study groups, discuss as a group, for you to bounce ideas around. Okay, so this is going to be in Canvas. I'm going to open a discussion forum for the whole class. Okay, so this is not a study group mediated by me. No, this is a study group encouraging you to discuss with your classmates. Okay, so I'm going to open the discussion forum in Canvas for this. And then on Thursdays of every week, you're going to have a self-paced review of whatever was discussed in the videos posted on Monday, and then you're going to take individual assessments in Canvas. Okay, so that's going to be the flow of our classes every week, right? So this is the proposed schedule. Now, last week, course introduction. So I just posted this, and then for the second week, which starts now, we're going to discuss units 1 and 2. Okay, next week we're going to discuss unit 3, and then after that you have 1 day for review, and then you have your examination. Right, and then weeks 5, 6, and 7 follows the same pattern. So we discuss unit 4 and 5 on the first week of finals. Second week of finals, we discuss unit 6. Last week of finals, the first day would be review, and the second day would be exam. Right, so take note of the important notes here and the dates, right? So you won't be confused as to when are the examinations and all of that, right? So your requirements are just midterm and final exams, enhancement activities, which I will usually give right after every lecture, and then of course assessments, which are going to be done every Thursday. Okay, and then for references for the course, you can have these 3, but of course you can have as many references as you can, as long as it's relevant to the topic, right? Now, yeah, so like I said, for those who haven't been my students, this is my name. I have an MSCS, and yeah, you're stuck with me. What else do we need to say here? Just a reminder, since you're taking this course on the first half, there's going to be another offering for the second half of the term. Now, I know that some of you are friends with some of the CS students that are going to take the subject on the second half. Now, yeah, so I'm probably going to give the same course, the same course activities and the same lectures. So I'm discouraging everyone to share the answers to your friends who's going to take it on the second half of the term, because it's going to be at your disadvantage. You get low scores, for example, on our quizzes and our activities here, and then if you give them the answers, then they get perfect. They get a higher score and a higher grade than you. So lugi kayo, diba? So yeah, just a reminder for you to be academically honest and don't share your notes or your quiz answers and seat work answers to your friends who are going to take the subject on the second half of the term. Okay, so yeah, like I said, I posted already some important notes on the Facebook group. So you only contact me using Canvas inbox. Okay? Academic concerns. If you feel that you have concerns that are non-academic and I can help you out, you just send me an email. You already have my email. I'm going to post that on the Canvas homepage as well. Okay? All right. So let's start with our lectures for the course. Okay. So let's start with Unit 1. So this is fundamentals of computer design. No? So as an introduction to design, we start the course with this quote by Bill Gates. Now, this is what he said. I think it's fair to say that personal computers have become the most empowering tool we've ever created. They're tools of communication, they're tools of creativity, and they can be shaped by their user. Now, the most important part that concerns us in this course is the last part here. They can be shaped by their user because as you can already see, since you are Gen Z, I suppose, no? So you grew up with all of these technologies already existing, right? So no matter what problem there is, you can potentially solve it using a computer as long as you know how to shape the computer or design the computer to solve that specific problem. Okay, so that's what Bill Gates was trying to say. This is why computers are very powerful. No? They can be anything. They can be tools of communication, creativity, and anything that can help us solve whatever problems we have, as long as we know how to shape them properly. Okay, so this is why it's important to learn about computer design. Okay, hardware and software design. Okay, so here we have an introduction to that. No, introduction to design. The introduction to design, we talk about performance improvements. How does new designs improve on previous designs of computers? Now this hinges into major events. The first one is the continuous improvement in semiconductor technology. Okay, first here is continuous improvement in integrated circuits. When we say integrated circuits, these are your chips. Okay, any of the chips that run your various machines are integrated circuits. Now they can be used as your central processing unit or CPU. They can be used as your GPU or graphical processing units, and some memory modules as well. Right now, here I would like to have an introduction on the difference between a single processor and a multiprocessor. Okay, so a single processor is just one CPU, which means that you only have one chip that's inside your computer to handle all of the instructions, to execute all of the instructions. Okay, that's single processor. A multiprocessor, which is what we have commonly now, even in your phones, is a chip embedded with many other chips inside of it. Okay, so there. This is a multiprocessor. Now, this is where the term cores come in. Okay, because if you have this chip, we're just too it's too, what do you say, this funny to call this a multiprocessor, right? Because this is your main processor and you have many processors inside of it. So it would be weird to call it multiprocessor, right? So what they did was to call all of these chips inside the chip as cores. Okay? So your multiprocessors now have a single chip with many cores inside of it. Now, depending on the one manufacturing the chips. Okay? So you have multi-cores. Now you have quad-core, dual-cores, and all of that. We're going to discuss those specifically when we go to parallelism at the later part of the course. But I just want to be sure that everyone knows the difference between a single processor, a multiprocessor, and what is a core. Now, because most commonly, students would go in and say that your computers have dual core or quad core without understanding what cores really are. Okay? So cores are just small chips inside your main integrated circuit in your CPU. Okay, so there. But how do improvements in integrated circuits affect the development of computers in the long run? Now, the main feature or the main function that we take a look at in this is the feature size. Okay, so the feature size of your chips. Now, when we say feature size, it's just the size of the elements on the chip. Now, mainly it's the transistors measured in nanometers. Now, your transistors are the main fiber of your digital design. Okay, so inside your chips, transistors are usually fibers that are very, very thin. This is nanometers, so it's 10 raised to the negative 9, right, of your meter. So it's very thin. We'll get to a comparison later on. But your transistors fit inside of the chip. So we have here an expression that I wrote. The lesser the feature size is, the higher the number of transistors you can include per chip. Okay, so this is the main basis of our improvements in computer technology. Okay, the more transistors you can fit inside the chip, the faster it can execute instructions, right? So the thinner your feature size is, the higher the number of transistors you have. Okay, so let's have a comparison of how thin these transistors really are. Okay, so for reference, the human hair is approximately about 75,000 nanometers. Right? Currently, we're using silicon as the main element for our transistors, and the atomic size of silicon is 0.2 nanometers. Now, through continuous improvements, the transistor size in 2019 has been reduced to 10 to 14 nanometers. So we're getting closer and closer to the atomic size of silicon, right? In fact, Samsung and AMD in 2019 already had processors that have 7 nanometers in transistor feature size. Okay? That's 7 nanometers. If you compare that to the 0.2 atomic size of silicon, it's very, very close already, right? Which is why additional experimentations have been going on to replace silicon as the main element in representing binary. Because remember, all instructions your computer executes should be in binary. So anything that can be flipped on and off, anything that can be represented as a 0 or a 1, can potentially be an element, a base element for your transistors, right? So we've had experiments in the electron and proton level already, right? Where they're experimenting if you can have a computer that takes in stimuli so that you can represent ones and zeros as protons and electrons. So I'm not really sure how that's being done, but I think that's one of the most recent experimentations that they're doing. Okay, because we're nearing the atomic size of silicon already. Okay. Yeah. So as a comparison, the first processor in 1971, one of the first by Intel, is Intel 4004. Now that processor only had 2,300 transistors. Okay, so only 2,300 representations of zeros and ones. Okay, compare that to where we are today. The AMD EPIC Rome, released in 2019, has 32 billion transistors. Okay, which is why your computers are much, much faster now. Right? So this is in accordance with one law as well in computer science and IT, which is Moore's law. No? So I think I've already discussed this with some of you. Now, Moore's law states that every year or every 2 years, there's an exponential increase in the performance of processors, right? So we've been observing that ever since, no? So there's a new processor released today. After 1 year or 2 years maximum, there's a faster one that comes into play, right? So that happens because of this, no? Companies Semiconductor companies continue research to minimizing the feature size, and if these experiments and researches are successful, then they successfully have an increased number of transistors that they can insert per chip, no? Per chip. And if you have a multiprocessor, then all of the cores are considered as one chip as well, no? Which is why it's not impossible for you to have this 32 billion transistors. Okay? So this is a comparison. So this is an image of the Intel 4004 in 1971, and this is our integrated circuit of the AMD EPIC Rome in 2019. Okay? So that's how far we've come. Okay? So that's the first two considerations. The third consideration when we have semiconductor technology is considering the clock speed or clock rate. Okay? Now the clock speed or the clock rate is usually measured in cycles per second or hertz. Cycles per second. Now a cycle is just the time that it takes for you to switch a transistor from 0 to 1 or 1 to 0. Okay? So it goes on to say that here, dito muna tayo. The lesser the feature size is, or the thinner your transistors are, the higher number of transistors you can insert per chip, right? So if you have many transistors, it means that you can have many instances of cycles, no? So you can switch the transistors from 0 to 1 in a much lesser time because you have a lot of transistors inside the chip, right? So the higher the number of transistors are, the faster the clock speed or the rate is, right? And which means to say that after that it could equate to faster processing power, right? So for comparison, again, you have Intel 4004 in 1971. It had 740,000 hertz or 740,000 cycles, no? That it can do per second. AMD EPIC Rome is 3.4 gigahertz. So kilohertz is thousands, 1,000 cycles per second. Gigahertz is 1 billion, 1 billion cycles per second. So you can just see the difference already. Okay. All right. So yeah, that's the first consideration that we have when we talk about the improvement of processing power. So that's more on the hardware, no? So if you look at all of these, it's focused on the hardware. You have transistors, you have chips, you have integrated circuits, right? But of course, we can't consider computer technology performance improvements based only on hardware. So the second consideration that we have is improvements in relevant software. Okay, so this comes in two parts as well. The first part is the continuous development in high level language compilers. Okay, so if you can recall, in our discussions or in your discussions in CC2 and CC4, higher level languages are languages that are human readable and are subsequently compiled and interpreted into binary. Okay? So if you go on and improve the compilers and the interpreters, then the faster your programs are going to be translated into binary, and the faster it is going to be able to be executed by your CPU and your hardware. Okay, and also aside from that, operating systems. Okay, now operating systems, we're going to have a different discussion on this one on unit 3, okay, or 4, I think. But suffice it to say that the combination of hardware plus the improvements in high-level language compilers, plus the improvements in operating systems, um, led to the development of RISCs, okay, or the reduced instruction set computers, which is the classification of computer that belongs that encompasses all of your devices today. Okay, all of those are RISCs, reduced instruction set computers. These are computers that have an ISA or instruction set architecture that allows it to have fewer cycles per instruction. Okay, or CPI. We're going to discuss that in a different lecture as well. Okay, so like I said, together improvements on both the semiconductor technology and relevant software, which is composed of compilers and operating systems, enable the creation of all of the technology we have today. Lightweight computers, your phones, your laptops, your tablets, your smart equipment, your smart refrigerator, all of those. So in addition to lightweight computers, the improvements on both of these, hardware and software, semiconductor technology and relevant software, it also led to the development of programming languages that are created for a very specific purpose. Okay, so let's have a few examples of this. Now, so productivity-based managed or interpreted programming languages. For example, we have Go in 2009, which was developed by Google for its cloud application. So it's not a general programming language already. It's a specific purpose, custom-made programming language. Now, the only reason why you can have programming languages like this is because you have the improvements on both semiconductor technology or your hardware and your OS and your compilers and interpreters or your relevant software. Okay, so aside from Go, we also have Rust, which is a language specifically developed by Mozilla for their browser, and then Dart, which was created by sino nga ba to? Google then. No? So Google developed Dart for their back-end website applications. Okay? Specific languages na siya. TypeScript is developed by Microsoft for as an improvement to JavaScript. Okay? Now Julia is one of the most academically inclined languages. Now it was developed by Harvard and MIT for numerical and computational science research. Okay? Aside from that, we have Swift, which is developed by Apple for Apple applications. We have Hack, which is developed by Facebook to improve their PHP and web development. And then we have Crystal, which was developed by Manas Technology to improve on the Ruby language, no? So the Ruby programming language. So yeah, so aside from these, there are a plethora of programming languages that are developed today for very specific purposes. No? So the very main reason again why these are possible is because of the improvements on both hardware and software. Okay? Semiconductors, transistors, and chips combined with the development of high-level languages, compilers, and interpreters, plus operating systems. Okay? So there. So now we go to a trend consideration of a single processor performance of instruction set architectures. Okay? So RISCs or your reduced instruction set architecture started at about the 1980s. No? And then as per Moore's law, as you can see, every year, every 2 years, there's significant improvement in the processor performance because of the feature sizes of transistors getting thinner and thinner. Okay, and then if that's the case, then you can fit as many transistors inside the chip. If you have space in that single chip, then you can have a multiprocessor or cores inside the chip. No? So Moore's law has been followed, and you can see that the processor performance started to increase and increase up until you have the introduction of the multiprocessor at about the early 2000s and still increasing. Okay? But there are arguments that Moore's law is already starting to plateau. Okay? But um, I don't think that's the case really, because as you can see last year, um, AMD and Samsung successfully came up with 7 nanometers transistors, higher feature sizes. So I think it's still going to go on for a long while, right? So there. All right. Now, before we go to the definition of computer architecture, I want you to understand the concept of the von Neumann architecture diagram. Now, all of your computers are patterned or loosely patterned on the von Neumann diagram, okay? Where you have an input, so all of your commands, all of your clicks, all of your taps are inputs, and then um, if it needs help from the operating system, then the operating system loads instructions into the memory. Okay, so data and the program. So when you run the program to get your input, it usually loads instructions in your primary memory. Okay, some kind of primary memory. Mostly today it's the RAM. Okay, your random access memory. But there are many other memory addressing modes available out there, but usually it's the RAM. So you get the instructions based on the input, and based on your program you get all of the instructions, load it into the memory, and then from the memory the CPU here fetches all of those instructions and then processes it inside and then fires off the output after that, right? So that's the von Neumann architecture. So we're going to discuss all of this individually in the later part of the course, but I just wanted you to have an overview of how your computer works. No? So all of your computers work like this. Now you have an input, you load the instructions in the memory, and then depending on the algorithms, your central processing unit fetches all of those instructions, executes them, and then fires off all of your outputs, right? So now we go through the computer memory hierarchy. Okay, so before we move on, I'd like you to be familiar with this hierarchy. So we start with the registers. So and then we go through the cache, primary memory, and then auxiliary memory. Now the registers are your smallest in storage space. Okay, so we go from smallest storage space up to the largest storage space. So registers are mostly inside of your CPU and they have the smallest storage space. Cache is can be outside the CPU, can be inside the CPU, or can be existing in many of your applications, and usually interfacing hardware and software. They are a little bit bigger than your registers, and then you go on to your primary memory, which is usually your RAM. But it's not only RAM. Okay, there are many other memory addressing modes, but your primary memory usually pertains to the RAM. Now it's larger than both of these, and the largest in memory space is the auxiliary memory, or your drives. Okay, your hard disk drives, your SSDs, and any of your permanent storage devices. Okay, so that's the hierarchy when it comes to size. No, registers are smallest, and then your auxiliary memory or your drives are your largest, right, in memory storage space. Now when it comes to speed, um, registers are the fastest to be processed by the CPU. Now instructions or information from registers can be fetched by the CPU the fastest, because mostly, like I said a while ago, they exist inside the CPU anyway. Okay. Next is cache when it comes to instruction fetch speed, and then RAM, and then your permanent storage devices. Okay. So sizes increasing pababa, speed decreasing pababa. Okay, because the fastest speed is in the registers. So let's write that down. So speed, when we talk about speed, it increases ganyan. Okay, because the slowest in speed is your permanent memory, and then next is your primary memory, cache, and your fastest speed access is in your registers. But when it comes to capacity, oh, that's letter C, huh? When it comes to capacity, it increases pa ganyan. Okay? So registers are the smallest in memory or storage capacity, increasing up until there. And also we have volatility. Now, when we say volatility in memory, it comes with how much the value or data is changed in those storage spaces. Okay, so it's in volatility. Registers are volatile because they change. No? Values and registers constantly change. Also with cache, values can change at any given time. Primary memory is also volatile because it changes as well over time, and it can be erased. No, so that's another concept I forgot to mention. Volatility is not just about if, the speed of changes of the values. It's also about uh, deletion. Okay, because these three, they are volatile. So when you turn off your computers, the data in these usually are deleted. No, unless you have some sort of algorithm that stores it up until the next boot. Okay, especially with your RAM. No, every instruction loaded in your RAM is usually wiped out when you turn off your computer or restart your computer. Okay, your permanent storage or your auxiliary memory is non-volatile. Ano ba yan? And yeah, it's non-volatile because this is where your operating system usually is stored. No? So this is permanent storage. When you turn off your computer, andyan pa rin yung data mo. Right? But for these three, most of your data will be gone when you turn off your computer. Okay? Unless, like I said, you have some sort of means to keep those information stored. Okay? So, yeah. So that's your computer memory hierarchy. I'm explaining this before we go to the old view of computer architecture definition, no? Because you need to understand that. Okay? So there. Now, the definition of computer architecture has evolved. Now, there's an old view and there's a new view. Now, the old view is that it's commonly based on instruction set architecture design. Now, ISA. When you say ISA, it mostly deals with yung diniscuss natin. So, decisions regarding registers, memory addressing, or how you fetch or get information from your memory addresses, what mode or addressing modes you use, and then what instruction operands are allowed in that specific architecture. Okay, and then so an ISA is defined as the interface between software and hardware. So if you have your transistors, you have your chips, your integrated circuits, you need to have so hardware is just hardware. No, it's really useless without software managing it. No, because for example, you have an integrated circuit with 32 billion transistors. Those will be useless if you don't have some sort of software that can turn those transistors on and off, right? So this is where your ISA comes in. No? So it's the lowest level interfacing between the hardware and the software, right? So your ISA, it can be differently implemented by the manufacturers of your chips. Okay, it defines what data types are supported, the state supported of your main memory and your registers, their semantics or how you fetch data from it, how you write data, and then instruction set, and then the input and output model that is used. Okay, so here don't be confused with instruction set and ISA. Now, instruction set is the minimum number of valid instructions that you can use to manipulate your hardware. Okay, and combine that with all of these data types, semantics, then you have an ISA. Okay, and again, the ISA is the smallest level or the lowest level of interface between your hardware and your software. Okay, so yeah, keep in mind hardware is just hardware. Okay, without some sort of software to maximize or optimize that hardware, it's usually useless. Okay, so that's the old view of computer architecture. Yung titingnan mo lang yung ISA, and then the data types, and then addressing modes and all of that. But we've come up with a new view, no? Because generally ISAs can be classified as either CISC or RISC. Now CISC is a complex instruction set computer. RISC is reduced instruction set computers. Okay, so mostly all of our machines now are generally RISCs, no? Reduced instruction set computers, which is why the real or the most newest view of computer architecture is we take a look at the specific requirements of the target machine. Because remember, on the very first slide, we said that we can shape the computers. No? So it's not really fair to define computer architecture based on just the hardware part. Okay? We need to take a look at now the specific requirements of the target machine, and to design it to maximize performance within the constraints of three major points. First is cost, second is power, and third is availability. Okay? And then, of course, we also include the ISA and the microarchitecture and the hardware, but we don't really rely on it alone. Okay? So here, we consider cost because, of course, depending on the target requirements and the target purpose of your machine, the different costs will be involved. And then power, because we consider how much power we need to achieve for the computer to achieve what it has to achieve. Okay? And of course, resource availability, both in hardware and software. And then we add that on top of the ISA. Right? So that's how we currently view computer architecture today. Okay? All right. So we move on. So considering that, we now move on to the classes of computers. So considering those three, we try to look at the different classes of computers based on those. Right? First, we have personal mobile devices, or PMDs. You have smartphones, tablets, and your ebook readers. The design emphasis of this is on energy efficiency and real-time processing. No? So we don't really rely on storage space, for example, or graphical processing unit or power, for example. No, we don't really rely on those when we create these types of devices. We just want it to be energy efficient and that the response time is fast. Okay? So, but it's slowly changing now because your smartphones today are can be considered as powerful computers, no? Compared to the smartphones before, in the early 90s and early 2000s. Okay? Of course, we have desktop computing, your personal computers, and your laptops. Your design emphasis is on price to performance correlation, because these are your most used consumer products, your desktop and your laptops. Okay, so when manufacturers design these types of computers, they put emphasis on the correlation between your price and your performance, which is why when you're buying your devices, especially when you're buying your computers, you try to look at the specs as compared to the price. Third is servers. Now, servers it can be database servers, web servers, application servers. They are usually designed based on 3 points. You have availability, scalability, and throughput. Okay. Now, availability comes with redundancy. In CC10, you learned this. Now, availability of a server comes in redundancy. So you should have backup servers so that if your one server goes down, you have another server to cater to your clients. Okay. Scalability, on the other hand, has to do with how your servers respond to the timing and the amount of requests. No? So for example, if you have an overload of client requests sent to your server, how is your server scalable enough? It can it manage maximum requests, or would it shut down? No? Would it be overloaded ng mas madali? How does it manage all of those? Timing and number of requests. So that's scalability. No? So when they design servers, they consider algorithms to manage that. And of course, throughput, the amount of data processed over time. No? So the amount of clients served over time. No? So those three are your main focus, or are their main focus when they create servers. No? So you can already see the differences. When you create laptops, you don't really focus on these three. Right? But when you create servers, you have these design emphasis. Right? And then we have clusters or warehouse scale computers. These are warehouses full of common computers to provide services through the cloud. Right? So they're used by companies to offer software as a service. Now, these are your subscription services, subscription software. Not that instead of buying the software, they just allow you to subscribe the software. So these companies usually have clusters or warehouse scale computers. Of course, their design emphasis is also on availability, because they're offering it through the cloud, so it's stored in their servers. And of course, the price to performance correlation. Okay? And under this, we have supercomputers. Supercomputers are computational science and research focused. So, focused on quantum mechanics, molecular modeling. They are very different types of computers altogether, because they focus on FLOP, or floating point performance, and fast internal networks. Because when you're modeling and you're trying to break through the current limits of what computers can do, you conduct millions and millions of computations, no? Which is why your supercomputers are focused on floating point performance, right? And I think this is the last, I don't know. Embedded computers, on the other hand, those that make all of your everyday gadgets smart, like your cars, vending machines, ATMs, home appliances, video game consoles, network devices, all of that, they mostly just rely on price. No? You design this based on price, right? Because mostly they come in quantity, right? So there. Yeah, so as you can see, all of these different classes of computers are now more relatable to the new view of computer architecture. Where is it? Which is this one. Okay? Aside from the old view, instruction set architecture, and microarchitecture and hardware, we also consider cost, power, and availability. Okay? So, yeah. And based on that, we can now go to Unit 2, which is power, energy, and integrated circuits. Okay? We'll discuss this in a bit. Okay, so now we go to power, energy, and integrated circuits. This is going to be a very short lecture, but your quiz is going to be about this, right? So after this lecture, expect a short multiple choice quiz in Canvas. That's what you're going to do for today. So just go through the lecture again and then answer the quiz in Canvas. Okay? For next meeting, we're going to have a problem solving type of quiz based on our lecture here in power, energy, and integrated circuits. Okay? So the problem or the consideration that we have when we have computers is how to get power in order for your computer to work, and how to get power out as efficiently as possible. No? Because it doesn't, just because your hardware is capable of having all of these billions of transistors, doesn't mean that you have to be continuously using all of them, right? If it's not really relevant for the situation. So you need to get power in efficiently, get power out efficiently. Now, power and energy. Energy is just voltage. No? So your electricity just converted into power. and power is just energy over time, right? Like your watts. There are three types of power to consider when we talk about your CPUs. Okay, the first is peak power. Now, peak power is just the maximum power your computer can handle. Right? So very simple. The next one is much more important. It's your TDP, or your thermal design power. Now, thermal design power is characterized by sustained power consumption. So this is power consumption that goes on uh, for a certain amount of time, considering the different tasks that your computer does. Okay, so the reason why TDP is important is because it's used as a target for power supply and cooling systems. Now, because if your cooling systems are not don't have a benchmark of your TDP, then you risk your hardware, your chips being harmed now by overheating, right? So the TDP is currently lower than the peak and higher than your average power. And your average power is just the mean power used between surges of activity and inactivity. Okay. Uh, so we have a note here that says frequency or clock speed or clock rate greatly affects power consumption. Now, which is very obvious because, like as we mentioned in the previous slides, frequency or your clock speed or clock rate is just the number of times now your transistors can be switched on and off from 1 to 0 per at a given time span, no, per second. So if you have, for example, our AMD ROM, EPIC ROM, you have 32 billion transistors. The frequency that you can switch all of those at the same time from 1 to 0 will greatly affect power consumption because your transistors need a specific amount of energy to be switched from 0 to 1. Okay, and it also says here that plateaued clock rate is based on air-cooled limit. Now this is just stating that the common ground for all of your processors to fetch and execute instructions and switch transistors from 0 to 1 is the limit it has when it's being cooled at room temperature. Now, so the hertz, the amount of hertz that your CPU can handle when it doesn't have a cooling fan is your plateaued clock rate. Okay, so that's what it means. Okay, now considering that you already have cooling systems, you already have cooling fans, and your TDP as a benchmark, some people like to do overclocking every now and again. Okay? When we say overclocking, it's just you increase the speed or frequency of a CPU beyond the recommended speed. No? So beyond the recommended hertz, no? the frequency. Sometimes it's efficient for a short amount of time because there's a huge burst in performance, no? Increase in performance. But it's not sustainable for you to be overclocked for long periods of time because you run the risk of harming your CPUs or your hardware. Okay. So it's important to know that the clock rate can be reduced dynamically to limit power consumption. Now, dynamically meaning depending on the situation, depending on what your computer is trying to execute, you can reduce the clock rate dynamically. Okay, you don't have to make use of everything all at once just because you can. That's what it means. Okay, so this leads us to the discussion of here dynamic power and energy. Dynamic power is just the dynamic energy is just the energy required to switch your transistors from 0 to 1 or 1 to 0. So the way we compute this is through this formula. You have 1/2 multiplied by the capacitive load multiplied by the voltage squared. Okay, so that's just the energy required, dynamic energy. Now, if you want to measure the frequency, the energy over time, I should say, of your system, then you have to measure the dynamic power. Dynamic power is computed as 1/2 capacitive load times voltage squared. So here, this is just the energy. Now we want to consider it over time. So we now take into consideration the frequency that your transistors are switched over time. So multiplied by frequency switched. Okay. What does clock rate reduce? Power or energy? No. In the basic sense, it reduces the energy consumption. No. But since power is just energy over time, it indirectly reduces power as well. Right? So that once you reduce the clock rate, you reduce power consumption, you reduce energy consumption. Right? But which means to say that you can have different clock rates at any given time. Okay? Depending on the dynamic changes in your CPU execution, right? Depending on the tasks or instructions that you feed into the CPU, right? So yeah, so that ends unit 1 and 2. Now for today, after you watch this video, if you're confident enough to take the quiz already, then you can do so. If not, you can just replay and watch and take the notes and then take the quiz after. Okay. For next meeting, that's the time we're going to have your problem solving quiz. Okay. So I'd like you to focus on this dynamic energy and dynamic power for you to answer, for you to be able to understand and answer the problem solving quiz next meeting. Okay. So okay, that's it for this meeting. The quiz will be open. The quiz today will be open up until the end of the period. Any later than that, and you forfeit the quiz. Okay? So, yeah. See you next week.